want to take a look at one more example of an arc length parameterization, and that's going to be for a line. So let's just take a generic line. Let's suppose I have r of t is equal to r naught plus t times v. So r naught is my starting point, and v is my direction vector. Now, if I want to get the arc length parameterization, there's a very nifty shortcut. Because I basically know, okay, I'm starting at the tip of r naught, and I'm going in the direction of v, and that's going to give me my line. So every time a second passes, if I think of t as time, I have traveled the length of v, whatever that is. So at time 1, my arc length would simply be the magnitude of v. At time 2, my arc length would be the length of the line segment. Its length is 2 times the magnitude of v. So it seems reasonable that if I want to get an arc length parameterization, I would simply have to ensure that v was a unit vector. So that my arc length parameterization would just be r naught plus s times v hat. That would be v normalized. Turns out that's correct. If I make it so that my direction vector is a unit vector, then my arc length will simply be the length. Well, it's always the case that with a line that my arc length is just, if I'm using 0 as my reference point, is just the length of this t times the direction vector. That's how far I've traveled. And then if this is a unit vector, that would just reduce down to s. Let's actually see that that works out, though, by going through this process. So if I were to write things in terms of a dummy variable u, we would have r naught plus u times v. So r prime of u, now r naught is just a constant. The derivative of a constant is 0. This is a constant vector times my parameter u. I basically have the vector version of the constant multiple rule. That's just going to be v. Now, that's maybe a little bit easier to see with a specific example. So let's just suppose that I had r of u was equal to 1, 2, plus u copies of -3, 5. So there's my starting point, direction vector times my parameter. Now, if I just actually did the work to do the addition and the scalar multiplication, this becomes 1 minus 3u, 2 plus 5u. And when I take the derivative, you can see I'm just getting -3, 5. Oh, yeah, I'm just getting this. This didn't contribute anything, because when I took the derivatives of those constant components, I just got 0. This contributed exactly itself. So the derivative of a linear function is just the direction vector for that function. That's great, because the direction vector was sort of taking the place of slope. I know the derivative of a line is the slope of the line if I'm just talking about y equals mx plus b. But now with vector functions, the derivative of a line is the direction vector for that line. Now what that means is that the magnitude of r prime of u is just the magnitude of v. So that means that s of t would be the integral from 0 to t. I am using 0 as my reference point. I think I mentioned that earlier. Of the magnitude of v du. That's a constant. I'm going to get that constant times the length of my interval. And the length of the interval is just t minus 0, or t. Cool. Okay. So now I've got that s is the magnitude of v times t. I can solve for t. T is just s over the magnitude of v. Okay. So to get r of s, I'm going to take my formula for r of t, but I'm just going to replace t with this characterization of t. So that would be r naught plus t becomes s over the magnitude of v copies of v. I can rearrange that a little bit. That's r naught plus s times v scaled by the reciprocal of its magnitude. Oh my goodness, that's r naught plus s copies of v hat. So that does confirm our intuition that if I want to get an arc length parametrization for a line, just use the normalized version of the direction vector and you will have that.